you're here. Do you have any questions on what's been going on? Okay. So what I wanted to talk about today was what is known as quantum information theory. So, of course, a lot of what we've been doing has been studying quantum information, but in particular, this is the quantum version of the classical field of information theory, which is concerned with quantifying information and kind of sending it places. So, so let me start by talking about the concept of entropy. Now, of course, you know entropy from thermodynamics, but entropy also has an information theoretic side. And I'm not really going to talk about the connection between these two, at least not today. It's possible but unlikely that I will do so tomorrow. But the formula is basically the same, and there is a kind of a deep physical reason for that. But we're just going to focus on the information theory side of it. So, so the von Neumann entropy of a density matrix rho is usually written S of rho, and it's minus trace rho log rho. And inevitably, because we deal with qubits and other things like that, we're working in base 2 for the log. So this is a measure of kind of the amount of randomness that's in a density matrix. It turns out it's a generalization of a classical information theoretic concept called the Shannon entropy. And so the Shannon entropy is the entropy of a probability distribution. So we have, some set of outcomes, and outcome I happens with probability p sub I. And so then the Shannon entropy of this probability distribution is minus the sum over I of pi log pi. Okay, and you see that if rho is diagonal, which is a way of thinking of it as being basically classical, it's so that rho is a mixture, right, of orthogonal outcomes, of basis states. Then its eigenvalues are pi's, and trace of rho is 1, so that the pi's sum to 1, which means they're really a probability distribution. It's a positive semi-definite matrix, so all the pi's are greater than or equal to 0. Then this formula just becomes this formula, right? So the Shannon entropy is a special case of the von Neumann entropy. So the Shannon entropy, so how is this a measure of information? Well, if you're given a probability, if you're given a sample from a probability distribution, so one event happens out of this set of possible events, how much information do you learn by seeing what event actually happened? Well, if the probability distribution is very, very highly peaked, right, maybe even in the extreme case, there's just one possible thing that could happen. Well, then actually looking to see what thing happened doesn't tell you anything, right, because you already knew what was going to happen. And on the other hand, if this probability distribution is very spread out, that there's many possible things that could happen with reasonable probability, then actually finding out which one of those does happen is telling you a lot, right? You're learning something that you didn't know before. And so that's the sense in which this entropy is a measure of information. It's kind of telling you how much information was missing before that you now have once you see the outcome. Okay, and the Shannon entropy, the von Neumann entropy can be viewed as a measure of information in a similar way, although of course now it's a measure of quantum information. OK, so far so good. OK, so let's write down some properties of the entropy. Actually, let me do them over here. OK, so the first property, well, what's the maximum value that S of rho can take? So if we have a Hilbert space of dimension d, so that would be log of d qubits. Well, what's the maximum value? The maximum value happens when all the entries here are equal. All the probabilities or all the eigenvalues here are equal. And it's equal to log of d. So S of rho is less than or equal to log of d. And most of the time, I probably won't even bother writing this space 2. And the maximum occurs for rho equals I over d. So the maximally mixed state. So property 2. On the other hand, what's the minimum value it can take? Well, if we have a pure state, then, well, OK. So I mean, I said that this is a generalization of this. But actually, if you diagonalize rho, you'll always get something of this form. Of course, rho might not be generated by a mixture of basis states. It might be a mixture of non-orthogonal states or gotten by tracing over some entangled state, something like that. But anyway, so if you have a pure state, then there's one eigenvalue that's 1. And so you get a 0 here because 1 log 1. And the other ones are all 0. And 0 log 0, well, at least in the limit, as you get to 0, that's 0. So all of those get 0. And so for a pure state, the entropy is 0. So the entropy is always between 0 and log d. And moreover, there's a lot of bounds we can set on the entropies of regions. So suppose we have some composite system. So rho is the state of some whole, so the big system. And it's broken up into A and B. OK? And then we're going to say that the density matrix of rho on A is rho A, and rho on B is rho B. So rho A, of course, is the trace over B of rho, and rho B is the trace over A of rho. OK? And frequently, when I'm talking about entropies and whatnot, I won't write S of rho A. I'll just write S of A. So and so on. So using that notation, we have something called the Araki-Lieb inequality. Which you can also think of as a triangle inequality. And that says that if you have the entropy, so by this I mean S of rho AB, or in that picture just S of rho. This is greater than or equal to the absolute value of the difference, S of A minus S of B. OK? Let's see. So, and then let me write out the next one and then talk about this one a little bit more. So we also have a property called subadditivity. And subadditivity says that S of AB is less than or equal to S of A plus S of B. Okay, so so this one is maybe a bit easier to understand, right? If we have some uncertainty about what's going on in A and some uncertainty about what's going on in B, then when we combine them, the total amount of uncertainty we have is no more than the uncertainty of the parts. Okay. Now, in classical physics, the entropy of AB, so H of AB, can't be any smaller than the entropy of just A. Okay? Because if there's some randomness going on in A, you can't get rid of it by adding in B. Right? It might not be any bigger if A and B are totally correlated, but it can't be any smaller. Now, in quantum mechanics, that's not true, because in quantum mechanics, okay, it's easier just to think of the example, right? So what if we have a rho as a pure state, right? And then we have a part of that, but it's an entangled state between A and B. So part of that A will be a mixed state, right? So there will be some randomness there, and the entropy will be non-zero. But then when we purify it by adding B, we get a zero entropy. Okay? So that having the entanglement, the quantum correlations, can actually decrease the entropy of the whole. And how much can it decrease by? Well, it can decrease by, at most, the entropy of B. Right? And in fact, if you why don't I switch these order? So if you combine property 3 and property 2, then you can easily prove that for a global pure state, of A and B, then S of A equals S of B. Okay? Well, why is that? Well, we know that the global entropy is 0 because it's a pure state. And so we have the entropy of A as S of A, and it has to somehow get shrunk down to 0. So that means that S of B has to be at least equal to S of A. But by the same token, if we just look at start at B, take the absolute value, so we're doing the opposite direction here, it can only get shrunk down. It has to get shrunk down to 0, so S of A has to be at least equal to S of B. And so they have to be equal. Okay? So that's another useful property of the entropy. And then, so these, of course, are not enough to specify entropies. And there's one additional property that people frequently use. And all of these are not such a big deal to prove. This last one is kind of difficult, and it's a pretty important property of quantum entropies. And it's called strong subadditivity. So strong subadditivity is something about not 2 regions, but 3 regions. And it says that if you have the entropy of a region broken up into 3 parts, that it's less than or equal to S of AB plus S of BC minus S of B. And so the picture that goes with this is really if you have a Venn diagram like this with intersecting regions, and then B is the intersection, A and C are here. Okay? So, I mean, you can kind of understand this intuitively, that, well, if you look at the whole here, well, it could be S of AB plus S of BC, but then we've double counted the B region, and we're subtracting that off. And of course, because there can be correlations between these regions, the entropy could be less than that. But it turns out it can't be more. Now, the intuitive picture of saying, well, we have some stuff over here and some stuff over here, and we're double counting B is not right, because, I mean, again, entropies reveal correlations of multiple regions, like they can reveal correlations, and maybe there would be something weird going on that we don't expect. But it turns out that, in fact, that is a property that's correct for quantum systems, and it's just not that easy to prove. Okay? So any questions on entropy?
So strong subactivity implies subactivity.
Possibly. Let's see.
B empty.
If you take B empty, yeah, then it should be 0. So yes. Mm-hmm.
What do you need to assume to prove it?
What do you mean? I mean, you have the definition.
Like a subset of the previous properties?
No, it doesn't follow from the previous properties. I mean, it follows from the definition of the entropy. But if you just say, well, let S be some arbitrary function that has these properties, then no, we can't prove it. So I should say that actually there's many different kinds of entropies. Don't know if I'll have time to talk about any others, but there's Renyi entropies, which are kind of easier to calculate, but maybe a little bit less physically motivated. There's conditional entropies and relative entropies and all sorts of min entropies, max entropies, all sorts of things. And all of them have their uses. This von Neumann entropy is kind of the central one. All the others are kind of built around it to some level. And the von Neumann entropy is interesting for various operational reasons by itself, some of which you'll see today. But anyway, this is kind of the basic properties. So if there's any more questions on this, now's a good time to ask them. OK, so then let's move on. So let's talk about information theory now. And in particular, one of the basic tasks in information theory is data compression. So now we're talking about classical information theory. And so again, we have a picture where Alice is trying to send information to Bob. But in this case, there's no eavesdropper, there's no noise in the channel, nothing like that. Everything is perfect. And Alice just wants to use the channel as efficiently as she can. Okay? So in particular, Alice has some set of possible messages that she wants to send to Bob. And she wants to use as few bits as possible to send those messages. Okay? So for a concrete example of this, let's suppose Alice has let's start a new column. Alice has 4 possible messages. So she has A, which occurs with probability 1/2. She wants to send B with probability 1/4. She wants to send C with probability 1/8. And she wants to send D with probability 1/8. Okay? Now, if she just did kind of the straightforward, most obvious possible encoding she could do, she'd say, well, there's 4 possible messages I can have. So I would need 2 bits to encode that. Right? And 0, 0 would be A, 0, 1 would be B, 1, 0 would be C, 1, 1 would be D. Okay? So 2 bits. Okay, but she can look at this pattern of messages, and Alice and Bob, maybe they know ahead of time what the probability of each message is going to be. And she can say, well, the message A is much more likely than the other messages. The messages C and D, they're not very likely. So what if I use a very short message to indicate that it's A, right? Because that comes up most often. and then longer ones for the other messages. So for instance, I can say I'm going to encode A as just 0. Okay, if you get a 0, you know that it's an A. And then B, well, B has to be something that's different. I don't want to start it with 0 because then you'll think it might be an A. So let's start it with 1. But I don't want to stop there because then I won't have anything for C and D. So B will be 1, 0. Okay? And then C and D, well, I should start them with 1, 1. So you won't get them confused with A or B. But then I need something to distinguish them, so let's add a third bit. And C will be 0, 0, 1. D will be 1, 1, 1. Okay? So now, how many bits is this gonna use with compression? Oh yes, next page. Right. So that's an interesting thing. It's not going to be always the same number of bits. It's going to depend on which message I have. So the question is, how many bits will it take on average? So on average, well, I have probability of 1/2 of using 1 bit, and 1/4 of using 2 bits, and then, well, 1/8 plus 1/8, so it's another 1/4 of using 3 bits. Right? And so what does that add up to? Well, this is 5 quarters, and this is 2 quarters, so this is 7 quarters. So I've saved 1/4 of a bit on average by using this compression scheme. Okay? And if I only do this once, then maybe I'll get lucky and I've saved 1 bit. But on the other hand, I might get unlucky and actually have to spend 1 extra bit. So if you're just doing it once, it's not clear if this is something you really want to do. But suppose you're doing this 10,000 times. Alice is sending lots of messages, and each one of them is generated according to this probability. Then you're saving, 1/4 of a bit for each of those 10,000 messages, which adds up to be quite a lot, 2,500 bits. Okay, so that's where compression comes in. And this is actually a relatively small amount of compression, right? You can imagine a much larger amount of compression. So for instance, suppose we have a string of bits that's 99% of the time it's 0, and 1% of the time it's 1. Okay, and it's a very, very long string of bits like this. So if you're sending 1 bit for each of these things, suppose again you're sending 10,000 of them, then you have to send 10,000 bits. But because only 1% of them are 1, you're actually much better off saying where the 1s are, rather than for each one saying this is a 1 or a 0, right? And so say, oh, the first one occurs at spot number 50. Okay, and so that uses log 50 bits to say that. And the second one occurs at spot number 123. Okay, and so that's another small number of bits to say that. And by and large, you'll save quite a lot by doing that. Okay, it'll go down to, I don't know, roughly log 100 for 100. Sorry, roughly log 100 per message. Log of 1 over 100. Sorry, that's not right either. That's a negative number. Anyway, it's the formula. It's formula up there, as you'll see in a moment. Okay. Yeah. So in general, what we can do is we can say, okay, so let's imagine we're in the situation where we're sending lots of messages. We're sending lots of messages, and we want to see how many bits we can save by doing compression. Well, what we can do is we can say, well, so we have probability pi of message I. So out of n total messages, well, with very high probability, there will be roughly pi times n I messages. Okay? And you can run through all the I, and that's still going to be true. It won't be exactly pin messages, but it'll be, with very high probability, it'll be close. Okay? The probability distribution gets very highly peaked around one particular distribution of the number of messages. Okay? So the upshot is that if you look at the possible strings of messages, some of them are very unlikely, right? For instance, getting message 1 every time. Some of them, well, no individual string of message is likely. But if you kind of sum up all the message strings that have roughly pin type I messages, then collectively, that's very likely. Okay? So this is what's called a typical set of messages. And a typical set is basically defined as being some set of message strings that has total probability that's very close to 1. Okay. Now, obviously, what you're interested in is a relatively small set of typical messages. And then our compression scheme, known as a block compression scheme, is we're going to list the typical messages and assign bit strings to them. Okay? So I'll just write down in whatever order I like all of the messages in my typical set. So all of the messages that have roughly pi times n things of type I. And I'll count them. And the first one I'll send that as 0, 0, 0, 0, 0, 0. Second one is 0, 0, 0, 0, 0, 1. Then 0, 0, 0, 0, 1, 0, and so on. Okay? And therefore, the total number, and then anything that's not typical, I'll ignore them. Okay? Or alternatively, you can use some extra bits, sort of like in that case, to have a less efficient way of describing the atypical messages. But let's, for the moment, say I'll ignore them. And then Bob, on the other side, he gets this compressed version. And he'll take the bit string that he receives and go back to this lookup table and figure out which typical message it corresponded to. Okay? Now, if it was an atypical message that Alice was trying to send, then Bob lookup doesn't mean anything, because Alice just put in something at random, or maybe she put in a message that said, sorry, it doesn't work. I got an atypical message. But the probability of that is very small. Okay? So almost all the time, Bob will, in fact, be receiving a typical message, and he'll decode it correctly. Okay? Yeah?
The idea here is that you're sending enough information that's so you kind of you have to store so much data in the lookup table.
Well, yeah. So the lookup table, yeah. Okay. So the lookup table is the protocol. Okay. And so that's not counted as information that has to be transmitted. That's something that you've kind of arranged ahead of time. Now, in practice, you don't really want a big lookup table. You want some algorithm that lets you say, oh, given this sequence of messages, I can convert it to a string that I can send. Okay. But that's, yeah, that's kind of a little bit beyond the scope of what I wanted to do. Yeah?
So you are, if you have a long message, you are going to break it into chunks, right? Like, I mean, if Bob is trying, or if Alex is trying to compress, a book, she's not going to.
That's right. So if in a block compression scheme, that's what you do. Now, there's other kinds of compression schemes that don't really work that way. And in fact, this one that I was showing you up there, we have this variable length encoding, already doesn't kind of work that way. In that case, there's a specific encoding for each message, for each individual thing that gets sent. And then I can just kind of tack on as many as I like. And it will work out in more or less the same way.
Whereas here, it's like if you're sending a book, so these 400 characters, are a typical message because they're like 5% E's and 30% S's and stuff. Just,
right.
If something is like 37% Z's, then there just isn't a code for that. You just have to send it.
You're right, in this case. Okay. Yeah. Whereas in the previous case, there is a code for it. It's just it'll be much longer. Mm-hmm. I mean, the other advantage of the things up there is that so in this case you have to look at whatever your chunk size is, 10 pages, and you have to count all the letters in them and figure out what the encoding is. In the code up there, you can look at each letter one by one and send it. So that has a lot of advantages. This is just conceptually easier to explain how it works. Sorry, there was some other question up here somewhere. OK.
Can both of these be combined? So like you're assuming that each typical message is equally likely, right? Or like we're
yeah. So right. So I'm assuming that, but it's OK. So there is a model underlying this, which I suppose I should write down somewhere. So so the assumption is that each message is drawn from the same probability distribution. And is independent. So what that means is that the probability of getting message B for the second message is always a quarter, no matter what the previous one was, and that if I look at the 10th message and the 233rd message, they all use that same probability distribution, or this more general one. And so this is known as an IID source. IID for independent, identically distributed. And so given that assumption, it's actually a statement. I mean, it's a mathematical statement that all of the typical messages have the same probability, roughly. Okay, and you can calculate it, which I'm not actually going to do, but oh yeah, I will. Okay, so I mean, it's a trivial calculation. So what's the probability of getting ni messages of type I? Sorry, that's not what I want. So I want the probability of some particular string of messages that happens to have ni messages of type I running over all I. So what's the probability of that? Well, the first message is type 1. And so that has probability P1 of happening for the first message. The second one is type 2 and has probability P2. And the third one, maybe that's type 1 again, that had probability happening of P1. Okay? And so the probability of getting all of this is the product of all of these things. And I'm going to have how many PIs I'm going to have? I'm going to have ni of them. Right? So the total probability here is the product over I of Pi to the ni. Okay? And so when ni is exactly equal to n times Pi for all I, this probability is always the same, okay, regardless of the order. And that just comes out of the IID source. It had to be symmetric under the order. Now, when it's slightly off, then that's not true anymore. And so then the probability is indeed slightly different. And it's true I'm not taking advantage of that. But it turns out that there's not much you can be gained by taking advantage of that. Maybe some kind of subleading stuff. So anyway, so So the other thing that's interesting is the question of how many messages there are in this typical set. And actually, that's very interesting because that's going to tell us how many bit strings we need to describe them all. Well, you can figure that out. So, so if we're looking for the exactly typical messages, the ones that have exactly ni equals pin, well, there's quite a lot of them. But it turns out, if you calculate that that it's basically 2 to the n h of pi plus some little o of n. So little o is like big O, except it's strictly less than for all constants. So it's a kind of sub-leading term. And you can calculate this just by writing down numbers. Let's see. So how many typical ones? So there's, yeah.
So if you were saying messages, say like there's some cutoff value with pi of ni, and we're saying above, and I guess you set that to 1. Saying if there's, if there's.
Yeah. So okay. So actually, so the cutoff for this, you have the cutoff that this difference here is little o of n. Okay. So this is how close I want it to be to typical. I mean, for some particular choice here, usually it's going to be 1 over square root of n, because that's what you get from kind of the random width. Sorry, not 1 over square root of n.
Sorry, so PIN here is the probability, is basically the number of messages of type I
that we expect to see. Right. And so my typical messages will be ones that are close to that have close to the expected number. So they'll actually have ni of things of message I. And how close should it be? Well, we expect just from random statistics that it should be about square root n away.
So you're talking about like the kind of global.
The global distribution, yeah. For this is a block compression scheme. So we're looking at a block of many messages.
Right. Like each message is a page, you're getting the block. Okay. I'll think about it. Please keep going.
Okay. Yeah. Anyway, so you can work out the exact number of messages of exactly this size, and then you take the limit as n goes to infinity, and use Stirling's approximation, and you get basically this. For whatever reason, I decided not to write that down on my notes, so I won't try to reproduce it right now. But the upshot is that we need n h of pi plus little o of n bits to send this. And in particular, when h of pi is less than its maximal value, we're saving over just sending the. So I mean, if the maximum value of h of pi, just like the maximum value of s of rho, is log of the total number of possibilities. Okay. And that's the number of bits we'd need if we were not compressing. We'd need n times log of the total number of possibilities for each message. Okay? And then when h of pi is less than that, we're saving. And that's what the compression is getting us. Okay? And so this fact is incorporated in kind of one of the main theorems of information theory, which is Shannon's source coding theorem. And it says, it says two things. So it says, first of all, it says this thing, that this is sufficient. So to compress n messages from an IID source with entropy H. And we want the asymptotic failure rate to go to 0 as n goes to infinity. So that's what I said before, that the atypical messages become very unlikely. So we need at least this number of bits. And there exist coding schemes. There exist compression schemes. Using only that number of bits. Okay? So this is telling us basically what the asymptotic requirement is, sufficient and necessary, for compression of information, at least from an IID source. And so this is one of the operational interpretations of the entropy. And you can see why it now has the meaning of information, right? Which is, in order to actually send information in the usual sense, this is really how many bits we need. And so that's telling you how much information in a practical sense, how many transmissions you need to kind of incorporate everything about the source. Okay. So since the example of language came up in one of the discussions, let me talk a little bit about that. So certainly in the English language, some letters are much more common than others, right? E is very common. Q is not so common, unless you're doing quantum information, in which case everything has a Q. But so if you calculate the entropy, you'll definitely get something less than log of 26 of English language. But the other thing about language is that it's not an IID source, right? If you do happen to see a Q, it's pretty likely that the next letter is going to be a U, right? So they're not independent. And if you see a couple of consonants in a row, it's getting pretty likely that you're going to see a vowel soon. So in order to do better in this compression scheme, you can do better than just taking the probability of each letter and treating it. You can look at the probability of words. Right? And you say, well, some words are more likely than others. But even beyond that, sequences of words. Some sequences are more likely than others. Even given that all the words are in them are likely words, for instance, it's still unlikely to see the sequence cow, house. Right? They're pretty common words, but together you don't say that very often. So real-life compression schemes try to take advantage of this kind of thing and the correlations in the language. I said that one of the reasons that we have high-speed communications is because of good error correction. But the other reason is because of good compression schemes. And certainly you'll see compression schemes kind of ubiquitously. Pretty much every format, file format, that you use nowadays for sending anything, PDF, JPEG, they're all compressed. Okay? And the better ones transmit faster. That's sometimes even obvious. Okay. So any more questions about classical compression? Yeah.
So in natural language, when it's clearly not IID, does that mean that there's some? Does that make it easier or harder to compress it? Like if we.
Well, okay. So so I think by and large you can do a pretty good job of compressing if you just do treat the letters or the words in an IID way. I mean, in principle, it could be that the correlations, let me think. Yeah, okay. And actually, I can even prove that to you. So suppose I look at compressing the words rather than compressing individual letters. Or let's simplify some more. I'm going to block off the words into groups of 5 and treat them as 5 letters in a row as one of my messages, as opposed to treating the individual letters as a message. So how much compression is that going to take? Is it going to take more or less? Well, by this property of subadditivity, I know that the entropy of a 5-letter block is going to be less than or equal to the sum of the entropies of the 1-letter blocks. Okay? So compressing as a group of 5 cannot take more. It can take less because there's correlations, and it will take less. But it can't take more. Okay? And so certainly you can do much better that way. I don't have any idea what the actual numbers are. But you can improve already by compressing at the level of single letters. And if you just kind of ignore the additional correlations, it doesn't hurt you, except giving up something, a further improvement that you could make. Okay?
Sorry,
Yeah.
Kind of confused over the definition of a typical message.
Sure.
What makes a like what's the when can I how can I like definitively cut my set into this?
Good question. You can't. It's not kind of an invariant property of the set of messages. Generally, what it is a property of the compression scheme. Okay? So the compression scheme is kind of saying this is a set of typical messages, meaning that the total probability of the set of messages is exponentially close to 1 as n gets large. Okay? And if different compression schemes have different typical sets of messages, that's generally OK. But what we do know is because the total probability of a typical set has to be close to 1, that if you take the typical set for one compression scheme and the typical set for another compression scheme, they're going to have a very large intersection. In fact, the difference between them itself has to be an atypical set, meaning the probability goes to 0 as n gets large.
When you say the probability goes to 0, like the probability of, when we talk about n, and it's a number of messages per second.
Yeah. So compression scheme, I mean, it's easier to talk about them as actually kind of a sequence of protocols for larger and larger n. I mean, in this theorem, there's an explicit limit that I'm imagining. Okay. So I have some sequence of protocols for larger and larger n. And so this typical set is not just for a single value of n, it's a sequence of sets for larger and larger n.
So you're saying that, like, I have a sequence of kind of, I have a compression of the blocks of messages as
Okay.
Thanks.
Yeah, so I mean, to kind of make everything precise and to prove this theorem, you have to go through and put in epsilons and deltas of, well, how high really do I mean by high probability? I want the failure rate to go to 0. How fast could it go to 0? Things like that. And that can be done. It's just I didn't want to bother with it because we don't have much time to talk about this stuff in the class. Okay. Are there other questions about classical compression? OK, so then let's move on to quantum compression. So we have kind of similar setup. We're going to have some IID quantum source. And with probability pi, it gives Alice, Alice gets the state psi I. And I should say that Alice doesn't know exactly what state she's getting. It doesn't tell her, oh, you're getting psi I. It just gives it to her. Otherwise, she'd kind of be getting a classical message, right? And so her goal is then, of course, to send this to Bob, or given some set of n of them, to send them all to Bob. And so we can describe this source with a density matrix, right? The state that Alice is getting is a mixed state, right? It's probability pi of psi I. So what she's getting is the density matrix sum over I, pi, psi I, psi I. Yeah?
Can you remind me what the second I in IID is?
Identical. So every time she's getting a state, it's drawn from the same distribution. OK, so right. So then she wants to send these to Bob. And kind of we want a similar statement that it should work almost all the time. But since we have various notions of distance in the quantum case, so it's in fact good enough. So in this case, we were kind of imagining that either Bob would get exactly the right string, or with very small probabilities, he might get something else. Okay, but in the quantum case, we can imagine Bob getting a state that is very close to the correct state, in the sense that it has high fidelity to the correct state. But now we have to be maybe a little bit careful about what we mean, because we're getting mixed states. I mean, we could say, well, the density matrix should have high fidelity. But suppose these states are being given to Alice by somebody who does know what they are, right? Then even if the density matrix is right, we might be concerned that the exact pure state, which is known to this other person, is getting messed up. So how do we deal with that? Well, the most straightforward way is to say there's some reference system which kind of keeps track of what state is being given to Alice. Okay? And then Alice transmit to Bob, and we want Bob in the reference system, the state of Bob in the reference system, to be close to the correct state. So in particular, what we're going to do here is we're going to give Alice and Bob a pure state, which is the purification of rho. So rho is equal to the trace over R of psi. Okay. And why is this good enough to incorporate all of these models? Well, I don't know if you learned this when you were talking about purifications in previous classes, but when you have a purification like this, there's always for any given mixed decomposition of rho like this, there's always some measurement that you can make on the R system that will produce this distribution on Alice's system. Okay? So for instance, well, okay, yeah, it's maybe, okay. So for instance, if you have a maximally entangled state here, right, 0, 0 plus 1, 1. On the reference system, you can measure in the Z basis, and you'll get probably a half of 0 for Alice and probably a half of 1 for Alice. Okay, so that's an example of the sort of thing. But if you make a different measurement, then you'll get different pure states for Alice. Okay, and by making any measurement you like, you can get you run over all the possible decompositions of rho into mixtures like that. So I'm seeing by your faces that this is new information for you. Okay, but it's a good thing to know. Okay, so the upshot is that this picture here incorporates all the possible distributions that Alice could get that have the density matrix rho. And so it's good enough to make this work, and then all of those other possibilities work as well. Okay? So our goal here is to preserve the fidelity of the full state with the reference system. So that's called the entanglement fidelity.
And was your argument similar to the relationship between teleportation and entanglement swapping?
No, I don't think so. I mean, entanglement swapping is basically using teleportation on half of an entangled state. This argument, I mean, it has more to do with a tutorial problem. Oh, sorry, that's not a tutorial problem. Well, it'll be one of your homework problems, I believe. So there's a relationship between kind of an entanglement-based quantum key distribution system and the BB84 system that I talked about yesterday. And I don't remember exactly what we put in the problem, but it's related to this question. Right, so high entanglement fidelity. So, which is saying that the state RB should be very close to the state RA, which is just this big psi. Okay, so but of course, we don't want it to be true necessarily for each individual. I mean, we want it to be true for the whole thing, not. So this is the output state. So the output state, of course, doesn't have to be an actual tensor product. The input state is by assumption, right? That's what it means to say it's an IID source for the quantum case. Okay.
So when you say close, do you mean like the trace distance is smaller?
Well, in this case, I'm saying high fidelity, but that also means the trace distance is small. Yeah.
These size are in general different for each n, right? Or like each size one message.
No. Yeah. So sorry. So this is. I'm assuming an IID source. Mm-hmm. So every time Alice gets a message, it's drawn from the same probability distribution, and so we have the same purification rho. I mean, so we have the same density matrix rho and the same purification psi. So it's always the same psi.
Okay.
Because it's an IID source.
Mm-hmm.
And when we do it n times, actually we have psi tensor n.
Okay.
That's what I was writing up here. Right. Okay. And then Alice will do some compression scheme, which I'll talk about in a moment. And then Bob gets some output. And then I want the collective output of Bob and the whole reference system for all of these n iterations to be close to this tensor product input state. Right? The output state, again, because the compression might involve some interaction between the different copies, doesn't have to be a tensor product anymore. And in general, I don't think it will be. But it's nevertheless close to one. Yeah.
Sorry, could you remind me the definition of fidelity?
Yeah. So for mixed states, it's this little complicated thing. And let me look it up so I don't get it wrong. So fidelity of rho and sigma is trace of square root rho to the 1/2 sigma rho to the 1/2. Okay. This, of course, is the fidelity between a pure state and a mixed state, which is a bit easier. It's just it's just this. Or maybe absolute value of that. Yes, square root. Square root. Okay. So other questions on what we're trying to do here, or what the definition is? Okay. So how do we do it? So that uses something called Schumacher compression. And the strategy is actually basically the same as what we did classically. So what we're going to do is we're going to diagonalize rho. And then run a classical compression scheme in the eigenbasis of rho. Okay? And you want to do it coherently, obviously, so you don't destroy superpositions. You need to run it a reversible version of this classical computation. And of course, you want to erase all the intermediate stuff. So again, not to destroy entanglement. But when you do that, then at the end, well, so whenever Alice is sending, so you can imagine measuring this reference system so that Alice is sending basis states, because that's a possible decomposition. And then Bob is getting basically the same basis state with very high probability by the classical compression properties. So the upshot is that, at least for that basis, it's very similar to the original thing. But it turns out that, in fact, you're even preserving entanglement and all that other stuff with whatever's going on. So it does, when you do this, it does, in fact, have high entanglement fidelity. And this uses how many bits? It uses n s of rho plus little o of n qubits. Yeah?
Just realized, like, all right, so the idea is that, like, a LSN's like a smaller density matrix to Bob. Bob then kind of reconstructs the bigger one from the small one.
Yeah, so in this case, we're doing block coding. So she's taking a whole n of these messages. She's doing some, well, it's not unitary because it's going to a smaller space, but she's doing some unitary transformation involving ancillas that go to some smaller Hilbert space, tensor some junk that she keeps that basically contains, information about the atypical stuff. And then she sends this smaller Hilbert space to Bob, who then does the inverse and gets back something close to the original. That's right. Yeah, so again, if Alice wanted to send this without compression, we have a d-dimensional Hilbert space for rho. And so she'd have to send log d qubits for each message. So we'd have n log d, which is the maximum value of s of rho. And so when s of rho is below its maximum value, we're saving. Okay? So maybe then to finish off, I will just comment that, so this compression scheme, as I've described it, assumes that Alice and Bob know what rho is. Right? And so they know what basis to work in, and they know what the kind of the probabilities of the basis states are, and so on. So they can work out the typical sets. But even that is actually not necessary. There's something called universal compression, classically or quantumly. In the quantum case, what you have to do is you have to say, well, OK, we're going to get many symbols eventually, right? Many messages. So for the first number of times, Alice is not going to try to be very efficient in compressing. But what she's going to do is she's going to make some kind of weak measurement on each one to try to gain some information about what rho is. Okay? And then eventually, she'll have a pretty good idea of what rho is. And so she'll know what compression scheme to use. She'll send a description of that to Bob. And then from then on, she'll use that good compression scheme. Okay? Now, again, there's a bunch of epsilons and deltas you have to look at to make this work right. But the point is that the description of rho and the description of the compression scheme, they're, well, not exactly constant size because you want the accuracy to get better and better as the system gets bigger, but pretty close to constant size. And so as you're sending many, 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 many messages, that initial phase is kind of negligible in size. And so that's why this universal compression works. So let me stop there. Are there questions? Yeah.
So in quantum compression, we are still trying to send the source has a density matrix, but ultimately we're trying to send like a string of qubits, right?
Sorry, you mean the physical thing that gets sent over the channel, or the messages, the underlying message of what you want to send?
Isn't the density matrix, right? It's the actual string of qubits.
That's right. That's right. Yeah.
So,
Yeah. I mean, so yeah, sort of. I mean, so I think it's important to be able to separate between kind of the physical realization of the message and the underlying state of the message. It's the state that she wants to send.
Well,
So for instance, in quantum teleportation, right? I say, well, you get out the same qubit at the end, but obviously it's physically a different qubit, right? It could be in a totally different system, right? So if you have an entangled state between I don't know, a photon and an atom, and then you teleport through this entangled state, the state of, and your input state is a photon. You do somehow you get an entangled measurement between these two photons, and you teleport. And at the other end, now your state is in the atom. Okay, so there's a mapping of the states of one Hilbert space to another Hilbert space, and that's the thing that we're trying to. And we're kind of modding out by that and trying to preserve the underlying state given this kind of equivalence that we've put in between the different Hilbert spaces. And we're doing that by going through, in the case of compression, by going through a medium of smaller dimension.
right. So I'm just trying to find the analogy between this and classical compression, because
Sure.
the density matrix tells me the probability. The density matrix is more like the probability.
That's right, yeah.
Message.
Right, that's right. But so this is why I want to have the purification. Because so in the classical, I mean, if you think of this purification in the classical case, well, there is no purification in the classical case, of course. But the closest analog would be to say, oh, there's a referee here who knows what the messages are that Alice is getting. And at the end of the day, Bob is going to be able to tell whether he got the right thing by comparing with the referee. And so we want the state of the referee and Bob to be close to what the referee and Alice had initially, which in that case was totally correlated. So that's, is that?
The big difference is that there, the message is just whatever Alice wants to send, whereas here, Alice doesn't actually know exactly what she's sending.
That's right, yeah.
Okay.
So
That's right.
like the way you've kind of written that setup, the idea is that the referee has, Alice is kind of the group of Alice and the referee. She might have the density matrix. The referee kind of contains the.
Well, sort of. The thing is that Alice doesn't have access to whatever the referee has.
Right.
So her compression is done completely on this state, on the density matrix state.
But like, I guess at the end of the day, we kind of think about this global size, or this global size containing all possible combinations of density matrices, and is splitting up into R and A, where R contains information about exactly which density matrix, which of the eigenvalues of the density matrix we're sending. But really, you could just do it the other way around. R could send that combination of the density matrices, kind of pass it through psi. And from the perspective of, like it's not in terms of
sorry,
like in terms of the idea of what's going on here. If R sets up just this density matrix that corresponds to whatever it's measured, and sends that to Alice, and Alice doesn't know this hasn't come from the global side.
That's right. And in fact, because of this property that I said, that R can make different kinds of measurements and prepare different ensembles for Alice. So that's called steering, by the way. R can just start out with the state psi and then decide later, long after all this has happened, which ensemble he actually wanted to send. So that's
But I was unable to like influence what he receives, right?
well, yes and no. I mean, so the density matrix that B receives is always going to be the same.
Right.
But from R's point of view, he can say, well, actually, that density matrix was a mixture of these things.
You can choose which basis.
And then he gets to even see which thing in the mixture it was. It's just that experimentally, there's no way that Bob by himself could ever tell, or Alice for that matter. Okay?
Thanks.
Yeah, so tutorial today, and then tomorrow's last lecture, we'll talk about, I guess, channel capacity with noisy channels, which obviously we've talked a bunch about in terms of error correction, but I want to talk from an information theory point of view, and about entanglement, quantifying entanglement. Okay.